is Nana and I'm from the Buddhi Academy. So today we'll continue with the chapter that is D and F block elements. So in our last class we have seen about the physical properties of the elements. So D block elements, they are also known as transition elements, and F block also known as inner transition elements. Now they are D and F because in these elements D and F orbitals are starting to filling up. Okay, that's why it is D and F block elements. So they are basically present in between S and P blocks. So this center part is known as this is the D block, which is between S and P block elements. So they have a properties similar to S and P block. That's why it is known as transition. They transit between S and P block. Okay. Then we have seen about their some of their properties, right? Now, the position in periodic table, as you all know, it is between S and P block elements. Then we have seen the electronic configuration. The first series of transition element, it is very important. We have to remember this first series, okay? Because based on this series are all the properties being explained here. Then we have seen general properties of transition elements, their melting point, boiling point, ionization enthalpies, okay, atomic and ionic radius, oxidation states, their trends, standard, their electrode potentials trends. So in today's class, we'll see the chemical reactivity, how chemically they react. So transition metals, they vary widely in their chemical reactivity. They can react with many things, okay. Many of them are sufficiently electropositive to dissolve in mineral acids, although a few are noble. These noble ones are the end molecules of the transition elements. Other than them, most of them are electropositive and they dissolve in the mineral acids. Okay. Now the metals of the first series, okay, first transition series, they are scandium till zinc. Okay, scandium till zinc are the first transition series. So first series, with the exception of copper, are relatively more reactive and are oxidized by 1 molar H plus ions. So copper, it cannot be oxidized using 1 molar H plus ions. Why it cannot be oxidized? We have seen it here in their electrode potential. See here it is explained ki copper has a unique behavior where it accounts the inability to liberate H2 from the acids. Okay. So though the actual rate at which these metals react with oxidizing agents like hydrogen ions is sometimes slow, even though they can be oxidized using H plus ions, but it is comparatively slow. Okay. This is how they react with chemicals. Now, there is another thing is that there is a decreasing tendency to form a divalent cations across the series. Divalent cations means you will not have something like Mn2, Cu2. Like for example, how you have N2O2. This kind of molecule is not possible here. So divalent cations are not possible, okay, in this series. The general trend towards the less negative E naught value is related to increase in the sum of first and second ionization enthalpies. So as I told you, they are negative E naught value, okay, or negative standard electrode potential. It depends on the sum of first and second ionization enthalpies, okay. Now next is the magnetic property. So magnetic properties means when magnetic field is applied, okay, to a standard, to a substance, mainly two types of magnetic behavior are observed, okay. If we apply magnetic field to any of these molecules or any of the substance, there are two kind of magnetism that is observed. First one is diamagnetism and second one is paramagnetism. Now, diamagnetic substances are repelled by the applied field, okay. Diamagnetic substances means they repel the magnetic field. If the magnetic field is coming like this, what diamagnetic substance will do is they will repel it, okay. They will repel it, they won't be attracted. For example, your magnets, two magnets, you can join them, right? There is a force of repulsion, they repel each other. So similar thing happens with diamagnetic substance, they repel each other. Whereas paramagnetic substances, they attract the magnetic field, okay. Now substances which are attracted very strongly are said to be ferromagnetic, okay. If the substance is attracted by the magnetic field, it is paramagnetic. If it is very strongly attracted, so it is very difficult for you to remove that, okay, it is very strongly attached to each other, that is ferromagnetic. In fact, ferromagnetism is an extreme form of paramagnetism, okay. Now, paramagnetism is the one which is mainly followed by the transition metals. Transition metal ions are paramagnetic in nature. Now, why they are paramagnetic? So, their paramagnetism arises from the presence of unpaired electron. Okay, basically the paramagnetism, it arises due to the presence of unpaired electron. Each such electrons having a magnetic moment associated with its spin angular momentum and orbital angular momentum. Now, each of such electrons, they have a magnetic movement. How they attract the magnet, or how they are attracted towards the magnetic field. So they can have a spin angular momentum or the orbital angular momentum, okay. They can spin within themselves or they can spin within the orbit also. So for the compounds of the first series of transition metal, the contribution of the orbital angular momentum is effectively quenched and hence is of no significance. So the first transition series, okay, they doesn't contribute to the orbital angular momentum, so there is only spin angular momentum which is effective. There is no orbital angular momentum, hence it is of no significance for the first transition element. So wherever the first transition element, if it shows paramagnetism, it is not because of the orbital angular momentum. Okay, for this the magnetic moment, okay, for first series, if it is not because of the orbital angular momentum, then what it is? So the first, for this the magnetic moment, okay, it is determined by the number of unpaired electrons and is calculated by using the spin only formula. So the paramagnetism, it is basically because of the presence of unpaired electron. Now how you will calculate the paramagnetism? For the first series, since it is not related to the orbital angular momentum, then the magnetic moment is determined by the number of unpaired electrons and is calculated by using a spin only formula. Now this is the spin only formula, that is mu is equal to root of n plus 2. So this is the spin only formula, okay, where n is the number of unpaired electrons. So n is number of unpaired electron, okay. You have to only know the number of unpaired electron to calculate the spin of the, or the magnetic moment of the molecule or the atom, okay. So this is the spin only formula where n is the number of unpaired electrons and mu, this part is, that is mu is the magnetic moment. So mu is the magnetic moment in units of Bohr magneton. Now any value should have a unit. So the unit of magnetic moment is Bohr magneton. Okay. Now a single unpaired electron has a magnetic moment of 1.73 Bohr magneton. If there is only one unpaired electrons, then the magnetic momentum, that is mu, is 1.73 bm. Bm is Bohr magneton. Okay. Now, the magnetic moment increases with the increase in number of unpaired electrons. Okay. Now, as I told you, it depends on the number of unpaired electrons. So, obviously, the magnetic moment will increase with the increasing number of unpaired electrons. Thus, the observed magnetic moment gives a useful indication about the number of unpaired electrons present in the atom. So, if you know the magnetic moment, if you don't know the number of unpaired electrons, but you know the magnetic moment, that means if the higher the magnetic moment, that means there are more number of unpaired electrons, because magnetic moment increases with the increasing number of unpaired electrons. So the magnetic moment calculated by spin only formula and those derived experimentally for some ions of the first row transition elements are given in this table. Okay, in this table they have calculated the magnetic moment according to the spin only formula, and these are the ones which are observed during experimental works. Okay, some of the, these are all some of the first transition elements. Okay, first transition series ka elements, these are first series elements. Okay, of this first series elements they have calculated the magnetic moment using spin only formula, and these are the observed magnetic movements. Okay, these are observed magnetic moments during some of the experimental work. Okay, these are derived during some of the experimental work which is which are carried out using this molecules. Okay, and these atoms. Now, formation of colored ions. Since transition metal have the ability to show colorations, okay, they show various colors. For basic example is copper sulfate solution. I hope all have seen copper sulfate solution. So it is blue in color. So copper is the one which is giving it that blue color. Okay. Now, when an electron forms a lower energy d orbital, is excited to a higher energy d orbital, the energy of excitation corresponds to the frequency of light absorbed. Okay, now here basically what happens when an electron from its lower energy, okay, d orbital ka lower energy, okay, lower energy d orbital is excited to a higher energy d orbital. Okay, lower to higher energy d orbital, when there is excitation of electrons from lower to higher level of d orbital, the energy of excitation, the energy required for that electron to jump, okay, this energy, okay, it corresponds to the frequency of light absorbed. Okay, this frequency generally lies in the visible region. Okay, this frequency of light absorbed, it generally lies in the visible region. Okay, now the color observed corresponds to the complementary color of the light absorbed. Now this color which is observed corresponds to the complementary colors which of the light absorbed. So the frequency of the light absorbed is determined by the nature of ligand. The aqueous solution where water molecules are the ligands, the color of the ions observed are listed here. So here are some of the molecules which are dissolved in aqueous molecules and their colors shown. So first two are, these two are of vanadium. Okay, this is manganese. Yellow color is for iron. This reddish color is for cobalt. Greenish is for nickel, and as usual this blue is of copper. Okay, now next is the formation of complex compounds. As I told you, the first transition series of this chapter is very important, is basically because they are able to form a large number of complex compounds. Now what are complex compounds? Complex compounds are those in which metal ions bind a number of anions or neutral molecules giving complex species with the characteristic properties. So a complex compound means there is a central metal atom, and surrounding that central metal atom there are anions or neutral molecules which attach to it. For example, iron. Okay, Fe. It has 26 electrons. It is atomic number is 26. Now, if you write the electronic configuration, so it will be 4s2 3d6. Okay, it will be 4s2 3d6. Now, 6 electrons it can take, right? In d orbital you can have 6 electrons. 1 2 3 4 5 and 6. So the remaining 4 electrons, okay, they require 4 more electrons to complete this orbit. So those 4 electrons are either taken as anions or neutral molecules which fill this electrons, okay, and complete the orbit. Now, this orbit completion, the compound which is formed is known as complex compounds. Okay. For example, here they have given FeCN6. Okay, what FeCN6 means? Fe, it has 6 numbers of Cn surrounding it. Okay. Now, CuNH3 4. PTCl4. So these are the complex compounds that are formed. Now the chemistry of complex compounds you can on the next chapter, that is coordination compounds. In the chapter of coordination compounds we will learn about this complex compounds. Okay, and the transition metals form a large number of complex compounds. Large number means most of the complex compounds are formed by transition metals. Okay, that too from the first series of metals. And this is due to the comparatively smaller size of metal ions, their high ionic charges, and the availability of d orbitals for bond formation. Now, why do transition elements form large amount of more the number of complex compounds is because mainly because of their comparatively smaller size, because of their smaller atomic or ionic radius, they are high ionic charges. Since the radius is small, they will have all the electrons will be attracted by nucleus where there will be high ionic charges, and mainly because of the availability of d orbitals. Okay, this empty d orbitals where electrons can be filled and they can form bonds. Okay, mainly because of the availability of d orbitals for bond formations. These three are the reasons why transition metals form most of the complex compounds. Okay. Now, the catalytic property. What is a catalyst? Catalysts are the ones which fastens any of the reactions. Okay. For example, any kind of reaction, if you want to increase its speed, you will use a catalyst which will not be involving any of the chemical reaction, but what it will do is it will fasten the reaction will take fast. Okay, so the transition metals and their compounds are known for their catalytic activity. Okay, they have a high amount of or high chances for catalysis. Now this activity is ascribed to their ability to adopt multiple oxidation states and to form complexes. Now why do they have this ability to perform like a catalyst? Is basically because of their ability to adopt to multiple oxidation state. As I told you, transition metals, they show various amount of oxidation states, right? For example, from +2 to +7, right? From +2 to +7 they can show oxidation state in a multiple forms, and another reason is because of their complex formation. Okay, vanadium oxide in contact process, finely divided iron in Herb's process. Now these are the examples of catalysts that are used in various reactions. Okay, vanadium, which is used in contact process, finely divided iron, which is used in Haber's process, nickel is a common catalytic molecule for hydrogenation, and think mostly you have heard about nickel, platinum, or palladium. These are all these three are transition metals and they are used as a catalyst. These are common catalyst. Okay, are some of the examples. Now, catalysts at a solid surface involve the formation of bonds between reactant molecules and atoms of the surface of the catalyst. Now, catalyst of a solid surface. Okay, if you add a solid catalyst to the reaction, okay, it involves the formation of bonds between reactant molecules and atoms of the surface of the catalyst. Now, first order transition metals utilizes D and 4s electrons for bonding. Now, here what they do is they bind to the reactant molecules. Okay, this catalyst, they bind to the reactant molecules. And for this binding, for first row transition elements, they basically use the D and 4s electrons for bonding. Okay. Now, this has the effect of increasing the concentration of reactant at the catalyst surface and also weakening of the bonds in the reacting molecules. Now, what this catalyst by binding to the reactant molecule, what they do is they increase the effect of concentration of the reactants. So, they increase the concentration of the reactants at the catalytic surface or the on the surface of the catalyst, and also they weakens the bond in the reacting molecules. If you have two compounds reacting together and you want only one of them to be transferred as a product, then you can use this catalyst where it will only bind to the ones which you want and the other one will be removed from the required product. Okay, now also because of the transition metal ions can change their oxidation state, they become more effective as catalysts. As I already told you, because of their changing oxidation states, they can become even more effective as catalyst. Okay, now these are some of the reactions why they can be considered as a good catalyst. For interstitial compounds. Now, what are interstitial compounds? Interstitial compounds are those which are formed when small atoms like hydrogen, carbon, or nitrogen are trapped inside the crystal lattice of the metals. Now, these interstitial compounds, okay, they are basically the compounds which are formed when these molecules, smaller molecules or smaller atoms like hydrogen, carbon, or nitrogen, are trapped inside the crystal lattice of the metals. Crystal lattice means something like this. There is a arrangement. Okay, they are connected like this. If these are all metals, these big circles are metals, and in between them, if any of the smaller atoms are trapped, so these are interstitial compounds. Okay, now they are usually non-stoichiometric and are neither typically ionic nor covalent. For example, TIC, Mn4n, Fe3H. Okay, this kind of molecules, okay, they are usually non-stoichiometric. Non-stoichiometric means you don't have to mention their numbers and all here, and neither they typically are ionic or covalent. Okay, they doesn't form a or they doesn't interact more with, or they doesn't hinder anything in the structure. Okay, now the formulas quoted do not of course corresponds to any of any normal oxidation state of the metals. Because of the nature of their composition, these compounds are referred to as interstitial compounds. Since they occur in between the metals, they are referred to as interstitial compounds. Now, the principal physical and chemical characteristics of these compounds. And now, what are the characteristics of this compound? How they react, or what are the things they are involved in? First, they have a high melting points, higher than those of the pure metals. So if you have an interstitial molecule or interstitial compound, they will have a high melting point than the pure metals. Okay, pure metals will melt easily compared to the interstitial metals. Now they are very hard. Some borids approach diamonds in hardness. Okay, some of these like diamonds. Okay, they use this interstitial compound formation for diamonds, in diamonds, for the hardness of the diamond. Okay, now they retain metallic conductivity even though they have interstitial, but still they maintain the metallic conductivity. They are chemically inert. Okay, they doesn't react with any of the molecules, they are inert. Now next is the alloy formation. Now what is an alloy? An alloy is a blend of metals prepared by mixing the components. Okay, alloy, it is a blend or a mixture. Okay, basically a mixture of metals, mixture of two or more metals prepared by mixing the components. Okay, alloy may be homogeneous solid solution in which the atoms of one metal are distributed randomly among the atoms or other. So alloys, they can be homogeneous where both of them are randomly distributed along with each other. Such alloys are formed by atoms with metallic radii that are within 15% of each other. So if you want to make a homogeneous metal alloy, then the atomic radius, okay, or the metallic radii should be within about 15% of each other. Okay, it should be smaller. Because of similar radii and other characteristic of transition metals, alloys are readily formed by these metals if they are of same radius. Okay, since they are of same radius, because 15% means almost they are of same radius. So if because of the similar radii, the characteristic of transition metals, alloys are readily formed by these metals. Okay, the alloys so formed are hard. So the alloys which are formed with similar radii, okay, they are hard and have and often have high melting point. So their melting point will also be high. They are hard and with high melting point. The best known are the ferrous alloy. Okay, for this homogeneous alloys, the best known are ferrous alloy, which is made up of chromium, vanadium, tungsten, molybdenum and manganese. These are the metal atoms which are used in the formation of ferrous alloy. Okay, are used for the production of variety of steels and stainless steels. Okay, these are the ones which are used for the formation of these alloys. Now, alloy of transition metals with non-transition metals such as brass. So here what happens, the some of the alloys which are formed from metals, mixing them with non-transition metals, okay, such as brass is made up of copper and zinc. As both of them fall under transition metals, you know that zinc is not considered to be transition because of its completely filled d orbitals. Another example is bronze, which is made up of copper and tin, are also of considerable in industrial importance. Even though they are made up of metal and non-transition metals, they are still considered important industrially. Okay. Okay, so these are the properties of the transition metals. So in our next video, we'll see about the oxides and oxoanions of metals. Okay. So thank you for watching my video. Please do like, share and subscribe to our channel.